Hello, thank you for taking your time to join us today. We are Team DOSE. I'm Clara Hall.
I'm Drew Bell.
I'm Ethan Yu.
Justin Mack.
Juan Nguyen.
Wesley Tip.
And today we will be introducing you to our proposed project, the Medicine Monitor. Our objective is to design a medicine storage container that stores both refrigerated liquid medicine as well as the standard pills and capsules. This medicine dispenser will also deliver medicine on a customizable schedule using an Arduino, remind the user to take their medicine according to that input schedule using both sensors and lights, and senses if the user has taken their medicine. In order to do this, Team DOSE will modify a refrigerator and create a temperature monitored medicine dispenser that contains 2 dispensing systems, customizable to a given schedule. In the top right of your screen, you will see a vague sketch of the concept of the medicine monitor. As you can see, there are 2 different dispersion systems within the refrigerator. For many people, taking medicine is a crucial aspect of their life, and oftentimes people forget to take their medicine or cannot afford a caretaker to help them with their daily routine. Furthermore, being a caregiver is a very time-pressing career, and traveling to someone's home to help them can be a daily struggle. Potential customers for this product would be both an individual who may need help taking their medicine or a caregiver who does not have the time or has a patient who cannot afford to pay them full-time. 50% of the US population forgets self-medication daily, and caretakers have skyrocketed in prices over the years. These are 2 large problems in our healthcare system that stops people from acquiring the help they may need. While there are some products on the market that offer solutions to these problems through pill dispensers, such as Hero Health, a scheduled pill dispenser, LiveFine, an electronic medication organizer, and Medicube, a customizable bulk-loaded machine that dispenses medicine, they are either too expensive, outdated, or do not offer variation in the medicine that can be dispensed. There are no products on the market today that offer a liquid dispenser for refrigerated medicine.
Our final design consists of 6 subsystems, which has 4 mechanical systems and then the electrical and CPE combined. The mechanical elements are distinguished into the cooling unit, first of all, which regulates the internal temperature according to a preset value. And that encapsulates the liquid and dry medicine handling and dispensary, which are the next 2 subsystems. So imagine a soda vending machine that takes the medicine and gets it to where you can access it, but it doesn't like drop it, it just dispenses it out. And then that liquid part involves motors and actuators, kind of like in a lazy Susan or carousel style, that turn the automatic turntable to get the liquid medicine. And then the dry is also a separate system with a belt feed mechanism to ration multiple medications. And both of those subsystems involve motors and actuators with different designs, but they effectively maneuver the correct amount of materials to the user or the patient who needs their medicine, even though those are separate subsystems. And then our 4th subsystem is the lock mechanism, which is our safety feature to monitor whether the door is being opened, unauthorized access. And it also will have either a mechanical lock or door monitor to alert when access is given that we don't want. And then the final 2 subsystems, electrical and computer engineering, is the power supply to the entire system, and then the controls and sensors, which will be controlled by the microcontroller. And that also has indicators that remind you to take your meds periodically. So the sensors will track whether the meds have been taken, and then the device will remind you using that system. And the user interface also syncs with an Android or iOS application that can be on a separate device. And the lock mechanism also involves electrical components. So say you have a patient who needs a morning pill and injection and only needs the liquid in the morning, but like has another pill like for the evening. So you would have your preset schedule for when it needs it, and then the system would only put out the pill that the user needs and the liquid medicine for the morning with some sort of reminder sound. And also could be an option to make it like a really annoying reminder, or you could just snooze it for like 5 minutes. And then if you don't take the medicine within that time, then the system would remind you again, you need to take your medicine. So like a flashing light or like a sound for people that aren't like in the room. And then that would also happen for the end. So the goal is to essentially reinforce the medicine being taken. And then if something doesn't happen, then we need to follow up with that, which leads into our critical paths. And that is what is the most important part for our risk assessment.
Our critical paths are essentially the parts that we are most concerned about. Our first one is the effective medicine storage and dispensation. Storing medicine is going to be a difficult task, especially for the liquid medicines, because those require a refrigeration unit and those can be difficult to work with. Secondly, the dispensation for both types of medicine will be difficult. You'll have to work with motors, belt feeds, and the dispensers as well, and they all have to go into the medicine grab tray properly. This will essentially encapsulate the entirety of the mechanical subsystem, and there are a lot of moving parts. A failure at any single one of those parts would result in the medicine not being properly dispensed, and so this is one of our critical paths that we are aiming to work on in our risk assessment. Our second critical path is for the user to customize a schedule for any medical needs they may require and have the device properly dispense the medicine at each of those times, and the correct medicines at that. This relates to the user interface and the Arduino programming. Our goal is to have the schedule be fully customizable, with any medicine being able to just be dispensed at any time the user desires. And this is going to take that's going to take a lot of coordination between the systems, and you want them to be able to access it at those times and only those times, so as to not improperly mess up a medicine schedule. Our third critical path is the reminder system. We intend to have the user be reminded to take their medicines both when they are supposed to and when the user fails to take at a point in time, and if the medicine happens to be improperly accessed. This will involve a sensor for medical dispensing and, most importantly, the user interface, both in the form of an Android application and visual and auditory alarms in the device. Working with Android programming, connecting to an Arduino is going to be new ground for our team, and is going to take a lot of work in order for us to get it working. So that is why it's a critical path, because we are concerned about the feasibility and the effectiveness of such a method. In conclusion, assessing these critical paths will ensure that our device is able to provide the effective medicine storage and dispensation, deliver the medication on the customizable schedule, and remind a user to take medication according to the set schedule, as we have described.
The specifications of our project we identified include the medicine storage, user interface, the liquid medicine and dry medicine dispensing systems, and the reminder or notification system. For the medicine storage, we determined the storage shall provide a space for liquid medicine and should provide a space for both liquid and pill medicine storage. This will ensure that liquid medicine is able to be stored and remain at an ambient temperature. For the user interface, the spec shall allow scheduling for a dispensary for 3 medications for daily use and should dispense 5 different medications at 3 different points during the day. This method can be observed and measured through the Arduino output and show our project has the ability to dispense medication for a patient at a desired time each day. The liquid dispensing spec mentions how our system shall deliver the correct liquid medication at the desired time with at least 80% reliability. However, should correctly dispense 100% of the time. This can be measured and validated through testing, observation, and data collection of accuracy. Similar to the liquid dispensing spec, the pill and dry medicine dispenser shall also dispense the correct dry medication at the correct user desired time 80% of the time as well, but should also correctly dispense 100% of the time, and also will be validated through testing and data collection. The final spec is a reminder and notification system, which states that the user shall be notified either through a light or sound indicator aligned with the user's desired program schedule and should go as far as receiving a notification on an Android or smart device. This is important in demonstrating that our device is notified to take the correct medicine at the correctly desired time from the user input schedule.
So after brainstorming, we have come up with a subsystem for our project. The bullet points are the ones that will be explained in more details because these are what we consider critical. The first one is housing. It will consist of mounting hinges and installations. The next one is a cooling system, which consists of sealing, leaking prevention, and defrost drains. Next, we have electrical subsystem, which will consist of processor speed, Android application, and user interface. And finally, the last subsystem is the refrigerated liquid medicine and dry medicine dispenser, which consists of the automatic turntable, bell feed, motors, and crab tray. And now I will explain the bullet point. First, in the electrical subsystem, processor speed. This is how quickly the processor compute information at maximum capacity. This will be a standalone. Next is the Android application. Whether the microcontroller is capable of connecting to and exchanging information with a handheld Android device. This will be a standalone. And next is the user interface. This is how the user can select medicine and maintain their daily dosage. Analysis will include code to make sure the daily dosage are not exceeded. Then, in the refrigerate and dry medicine dispenser subsystem, first, there's the automatic turntable. This is how the medicine in the refrigeration sections spins a given decrease every time medicine needs to be taken. Analysis will include calculation on a decrease that the turntable must turn with every comment, and ensuring that the turntable is given the correct comments. Bell feed. This is how the dry medicine will be distributed. Calculation include the amounts of torque needed and produced to turn the bell feed and distribute the dry medicine into the crab tray. Motors will be needed to turn the bell feed a specific amount to dispense refrigerated or dry medicine into the crab tray to allow user to take the medicine. This will be measured through how much power is needed to run the motors, and what kind of motor will be needed, the power needed from the electrical power source, and how much mechanical force is required to move the turntable. And at last, the crab tray. This is how the dispensed medicine will be available to the users at any scheduled time. This will be integrated to the fridge door and must not allow any cool air to leak. And in the next slide, we will cover the proposed critical path device.
On our proposed critical path, one of our biggest concerns for the dispenser as a whole is the ability to disperse the correct amount of medication to the user, whether it be a single pill or a precise amount of liquid medication. For our prototype, we will first focus on building two separate units, both a pill and a liquid dispenser, to demonstrate that the task is working in a non-refrigerated environment. Our secondary objective is to integrate these systems directly into the refrigerated door. For our electrical portion of the device, we are focusing our prototype to accurately detect and notify the user that a successful medicine grab has been completed via an Android app. We will focus on pressure or laser sensors to determine if the grab has been completed. It will also notify care providers in the event that failure occurs, also so that the patient still takes their medicine. For this portion to be tested and for it to be successful, at least one dispensing system will have been needed to be completed. Moving on to our critical features. From left to right, our electrical features, we will have our user interface and sensors that will be constructed into the front panel of the fridge door, which will be controlled by an Arduino device. Behind the door lays the majority of our mechanical components, where we'll have motors of various kinds to dispense the medicine onto a belt feed, which will then rotate towards the front and will reach the user. In the back of the casing, we will have our refrigerated storage system, which will hold all our medicine. Our main objective this quarter is to get the basic functionality of the interior components before building directly into the refrigerated unit. Onto our references, which shows the history and the data we collected to show that our concept is feasible. We want to thank you for listening to our presentation, and we are open to any questions that you may have. Again, thank you very much for listening to our presentation.